reciprocal lattice. I think it's an important class, and I'm surprised that a lot of people are not here today. But I hope the idea of the reciprocal lattice, you guys get a good handle on it, because it's absolutely important that you do for any kind of diffraction. Okay? And today I'll do some of the work on the board, and if I want to show better figures, I will show from there. So the main idea is that you all know the simple Bragg's law. Okay? So Bragg's law is n lambda is 2 sine theta. So I'm just going to write it here because I don't want to erase it very fast. This is E H by L. This is what we write, this is what we can. We can also drop this n, right? And we write lambda is 2d h, this is sine theta. We write it this in the general form. And here the order can be changed by looking at planes that have higher order planes that have the equivalent lattice spacing. So if you take this as your 1, 0, 0 reflections, you have a beam coming like this, getting refracted like that. So this, if it is 1, 0, 0 set of planes, you can have the 2, 0, 0 set of planes, right? You can have the diffraction from this. And basically, you can find an equivalent one for this order, a set of planes. So this would have half the spacings. So this factor, you can change it. So you can write this in general term without the n, because you can always find, if you do 1, 0, 0, you can, if you go to the second order, you find the 2, 0, 0 planes that has the corresponding diffraction. So we can drop this n and always say that we can find a higher order set of planes that satisfies things like that. So that's one key important point. Then the Bragg law has two important attributes of the planes that diffract. What are the two attributes of the planes that diffract that is included in the Bragg law? That's correct. This is what we call the orientation. Okay, so that's orientation. And what else? There is one more here that is related to the plane. That is the interplanar spacings. All right. So that is the key idea of diffraction. It depends. So, introduce a lot of conceptual ideas here. Like you can have the same diffraction. If you change the order of the diffraction, you can go back and look at a higher order set of planes that will satisfy. So you can drop the n in the Bragg reflection. As long as you understand that you can always select a set of planes. So strictly speaking, this will become, if you include the n, this will become nh, nk, and L. So if you take n is equal to 2, here instead of n, this is 1, 0, 0. Then if you go n equal to 1, this will become n 2, 0, 0. That's always multiply by 2. So that would be the strict rule, but we can drop all this NHK as long as we understand what we do. Okay? Is that clear to everybody? You should have seen this in college already. It's already in college. You should have seen this. The other important point is that reflection depends on two aspects of the planes. So we have to have a way to represent the planes that give you this information. Orientation of the planes and the interplanar space. So let's do a crystal here. This is I'm going to represent a lattice. And the lattice here, let's just take the first start with the unit cell that looks like this. Okay, let me just make sure I'm doing the so that it matches the damn thing in my book. Okay, So there it is. There is your unit cell, and here's your C-axis. So here's your A, here's your B, there's your C. What sort of a Bravais lattice is this? Is it cubic? Is it triclinic? Is it monoclinic? Is it orthorhombic? You guys have a sense of what it is? Two of the angles are 90 degrees. One angle is not 90 degrees. A is different from B, is different from C. What is this?
It's not. It's not rhombohedral. It's orthorhombic.
Go on. Take guesses. It can be only 6 of these, so you take a guess.
Orthorhombic?
No. Monoclinic.
Oh.
So monoclinic. So orthorhombic, the key element is set of 3 sets of mirrors or 3 sets of threefold axes. That's orthorhombic. Okay. But anyway, this is the monoclinic unit cell. Now we're going to do a lattice. So we're going to extend this. Okay, I'm going to extend this. So we're going to do planes. Right? You can also do additional planes like this. So, two sets of planes. So, in diffraction, what are the key ideas? The key ideas are we have to represent these sets of planes in such a way that we somehow encapsulate this interplanar spacing and the orientation. Right? So we need to encapsulate both of this in whatever representation we do. So what we do is we take this the interplanar spacing and we draw vectors that are normal to these planes. So here's a vector that we will draw. Here's a vector, for example, this vector, what is this? Is normal to A. This along this direction, this is normal to this. To these set of planes, we draw a vector. This set of planes, we draw another vector which is normal to that. So we put the origin here, we draw these vectors, and this distance that we draw, what is that distance? That we have to now encapsulate the interplanar spaces. That distance we draw here is the reciprocal of this distance. Okay, so that is the reciprocal is 1 over d of that. And this vector, the length, is 1 over the reciprocal of this distance. Yes? And so we have, from the origin, we do 1 point here. And the reciprocal of this distance would be that is the red one, the reciprocal of this distance. The smaller this distance, the longer this vector, the reciprocal space. Is that clear? So in this manner, what we have done, we have, yes?
Is it including those lines supposed to be 90?
No, it is just always normal to this set of planes. So this plane normal to this is this blue vector. This plane normal is normal to this. And then this one is normal to that. So if it's monoclinic, it won't be 90. If it's cubic, it will be 90. So you can see now the way I've done this is I've taken this one. This one is just the vector sum of these two. So in other words, we can now take this and basically draw the whole lattice like this. So, and this encapsulates the key important information that you have, that you need for diffraction. And the key information that you need for diffraction is this interplanar spacing. So we plot this interplanar spacing, this vector, as the reciprocal of the interplanar spacing. So what that one point encapsulates is the whole family of planes separated by that distance. It's not representing one plane, it's representing the whole family of planes that have that specific interplanar spacing. The concept clear that one point now represents the whole family of planes, not one single plane. And it tells you both about those, what is critical for diffraction, their spacing and its orientation. So if you have a crystal, you can draw the reciprocal lattice of that crystal, and the reciprocal lattice is attached to the crystal. So when you rotate the crystal, you are rotating the reciprocal lattice. So each point, each reciprocal set of planes is given by a point. So one way to look at the diffraction that you do is take what you do in Braggs law is that you keep the crystal the same, and then you rotate your incident beam. You can also do the other way around. You can keep the beam the same, and rotate the crystal, and then as you rotate the crystal, you actually rotate the reciprocal lattice. And so you can formulate the whole diffraction law in terms of the reciprocal lattice. That is called the Ewald sphere construction. That's called the Larrey criterion. This is what we do in the next class. You stay with this reciprocal lattice so you get familiar with the reciprocal lattice, and then we can, so this is the monoclinic lattice. It's very important to understand the reciprocal lattice construction, because this is the fundamental. As you go into more advanced approach to diffraction, we hardly use Braggs law. We always use the reciprocal lattice.
Can we label each plane family on that reciprocal?
I can do it in a second. Right now, just to give you the concept, I'll show you the slide and then we'll label everything.
Oh,
So
cool. Okay.
it's better for me to do it that way than draw it, because it's easier for me to just show you the slide. But the key point here to understand what the reciprocal lattice represents. We will do this now. After I show you the example, we will do this mathematically. Okay, so that you understand the structure of this in a mathematical way as well. It's important because later on you will see that it's the mathematics that matter. So this is what I was just saying. This is normal to plane one. We just don't call them anything. So there, this is the spacing. This is D1, and that is the spacing is D2, and this spacing is D3. And so this is how. So I should have labeled them 1 over D1, 1 over D2, and so on. So this is called strictly just D1 star. First we just call it D1 star, D2 star, D3 star, and then in a typical So this is the same thing now. So now I've indexed them. Okay, let me make this larger so you can see it. Okay. So you see now that is now the 001 plane, the 002 plane. This is now atomic A. This is C, and you have two planes, and then I take the reciprocal of that. So that is the 001 star, it's a 002 star. Now it's, if this thing is closer, the reciprocal lattice is further up. Because it's 1 over D, and then this is the D102, D10. It's always normal to those set of planes. And then you can form, just like you form the real lattice, you can form a unit cell which corresponds to the reciprocal lattice.
So A there is your real space. B is reciprocal space.
No, A, B, C is real space, and I will talk about the notation now. We always use A star, B star, C star for the unit cell in reciprocal space.
I mean the picture A.
Yeah, that is the, here, this is from the origin, this is A, that is C, B is out of play.
Right, so you have labeled 3 figures, A, B, and C. Figure A is real
Oh,
space.
you mean that within brackets, yeah.
Yeah.
That is the real lattice.
And then figure B is reciprocal space?
B and C are reciprocal space.
And C.
Yeah,
okay.
because what I've done here is that I've just shown you all the planes, what are the D spacings and the reciprocal of the D spacings. And then here's the unit cell, so you can take this one and draw the unit cell like that. So
Okay.
this is the 1, 0, 1, and then you draw the unit cell and you repeat this, now you can read it out.
Okay.
So, yes, any other questions? Everybody clear, or the only questions here? Any questions on this side? Okay, so this is really important to understand. Now what we're going to do is, we're gonna move this a little bit and switch it and talk about this mathematically. We are going to formulate a general way of calculating the reciprocal lattice for any Bravais lattice. And then, once we have that simple formulation, we know how to calculate the reciprocal lattice, and I will then give you some examples. Okay, so let me just close this again, and then we go back to the board. And now what I'm going to do is try to draw something in 3 dimensions. So this is, so we have a general crystal. Okay. So this is A, this is B, this is C. What sort of crystal you think is this? What sort of a lattice is this?
The monoclinic? No, it's triclinic.
Triclinic. The C is not 90 degrees. So now we're going to do and draw the vertical axis and draw the equivalent point here. We're going to label this the origin. We're going to call this A, B, and C. We're going to call this point B. All right, everybody is with me on this? So, what is the area of this parallelogram? This area is just the area is OABC. The volume of this is OABC multiplied by OP. Okay? And this is equal to the value of A, the vector A, so magnitude of this. I use normally this cross with a circle for a cross product. So you don't mix it up with a multiplication. So this is A cross B, this is the vector A, vector B, see, this is the real lattice, so this is the volume, and this is now this area multiplied by this height OP. What is the height OP? In terms of something we already have mentioned before? What is the height OP?
We have angles and length seats, so.
No, so these are 2 planes that are being separated by this distance. This is the D spacing, if you call this the C direction, it's the D of 0, 1. Okay? So now we have all the ingredients. So the way it is defined, the reciprocal lattice is defined as A star. We have three of them, B star and C star. This is in the most general case. It is defined in a cyclic form, B cross C divided by the volume. And this, wait, not write all at the same time. Because of the volume term, here's the B star, here's similarly cyclic C. If you do this way, you will never go wrong. C cross A divided by the volume. Yeah.
So what was the OB again? In terms of the things you already have, was that pretty good?
OB you mean?
Yeah.
OB is this interplanar spacing.
Yeah, I get that, but you asked us previously to like solve it in terms of things you already had, and then don't.
No, I just wanted to say something that you already know what it is, which is the interplanar spacing.
Oh, okay. Right,
What is this is something you already know, which is the interplanar spacing.
Okay, that's.
You're going to just solve it in a second.
Alright.
And then similarly, C star is, what is going to be C star now in the cyclic way? A cross B. So that's A cross B divided by the volume. Yeah.
The bar is on top of A, B, and C.
So that means it's a vector.
Oh, okay.
It's just a way that I write, because otherwise it will be a scalar. It's just, in the text you will have bold, but I cannot do bold, so I do a line.
Oh, okay. And then, so what exactly is the C vector there?
The C vector is,
Maybe label it and say that.
this is the C vector.
Okay.
I'm confused sometimes across OA, BC, or OB.
What's that?
For the volume.
Go across, it's multiple.
It's multiply.
Oh.
Multiply. That's why it doesn't have a circle.
Oh, is it top, was it cross? Okay.
Oh.
I didn't do it
It's
right.
multiplication.
I didn't do it wrong, okay.
Yeah, so that's why I make sure that I put the circle, so on the board, you can differentiate between multiplication and cross. Okay, so now we can put one of these together. So if you want to calculate the magnitude, so now if you want to calculate the magnitude of A, let me just use the same color so I don't confuse you. So if I want to calculate the magnitude of A star, then I take this magnitude of this, which is the area of OABC, and I divide by the volume, which is area of OABC, multiplied by OP, and therefore this cancels out to 1 over OP, and that is 1 over D. So the A star, the magnitude of A star is the reciprocal of the distance. So this is what we said before, and now we're just showing this mathematically. And so this is the general form for the reciprocal lattice. So if you want to do it mathematically, you take this, and the volume of this unit cell, the volume can be simply written, you can write it in any way. The volume, so that you have this in the notes, is A dot B cross C, the volume, or it can be B dot C cross A, or it can be C dot A cross. The volume can be generated mathematically in this form. So A cross B is just essentially this area, and it gives you the vector. You take the dot product of that, then you get essentially the volume. Okay? So in textbooks, you will see this not as a volume, but you will see sometimes this volume term written as A dot B cross C.
Wouldn't that actually be the formula for the reciprocal lattice of C? Since the area is actually the bottom.
You're absolutely right. So you're absolutely right. So this is what I've actually done is the C. But you're absolutely right. That was a mistake. You're absolutely right. C star. You're absolutely right. Thank God somebody's catching the mistakes. So, okay, so that's really just we're looking at the C direction. You're absolutely right. So then we can write any vectors, and this is just the units vectors. And so for any lattice plane, we can write that as a reciprocal lattice vector. And that reciprocal lattice vector would be written in this form. G, it's a vector. Either sometimes people use capital G, sometimes people use small g, it doesn't matter. And then, if you want to be careful, you can write HKL, so you know exactly what lattice vector it is referring to. And then it is given in terms of H times A star plus K times B star plus L times C star. So any vector here, so if you have this reciprocal lattice, it comes, see, this is the lattice now, we have points. This, you can take this vector, this would be your G, H, K, L, that would be given by H times A, E, and C, and you can write any, it's a lattice. Each of these points represents an entire family of planes. Now, this is what I mentioned before. We are talking about a concept that will come later. If you have an entire lattice of planes going up to infinity, you get a point. You get a zero-dimensional object, which is a point. If the reciprocal, the number of lattice points starts to shrink, this zero-dimensional point will start to expand. And then as it becomes really a very finite number, this one will have a finite dimension. And the dimension of this point will depend on the number of lattice points in that direction that you're interested in. And so this is important when you get to nanoscience, thin films, and so on. You don't have so many lattice points. So if you get to a small round object, you have maybe 100 lattice points. So there are only 100 lattice points. This will become quite finite in size. So if you have a long precipitate like this, in this dimension you may have a very zero-dimensional object, but in this dimension where the precipitate is thin, you will have an extended object. So it doesn't have to be spherical, it could have non-spherical shapes. And so, in order to get diffraction, as we will see, you just have to intersect somewhere in this reciprocal lattice. So even if you're very close to the diffraction condition, you'll get some diffraction signal because this reciprocal lattice point is extending beyond a finite zero-dimensional object. Yeah.
Is there at any point where a real sample becomes so small that a reciprocal lattice just becomes impractical?
No, it becomes really small when the object extends. So you have to have a very accurate diffraction condition for it to meet that. You have to have the angular range that you have becomes really, really small. You have to get exact scattering condition. And so, but if the thing is a little bit big, the angular range can vary a little bit and you will still get some diffracted intensity.
Okay, so the size depends really on your angle there.
Yeah, that's essentially what that will depend is the theta. When we talk about in reciprocal space, you will see. It's a very important concept, especially for nanoscience and nanotechnology and also thin films and so on and so forth. And so this concept is clear now. Okay. So let me do one more example of doing the reciprocal lattice, and we will do it for the cubic case, which is the simple case. Okay. So let's do that for the cubic case. We'll erase that part of the board. So let's do the cubic case. This cubic case. They're roughly the same. They're roughly the same. There's A. Okay. So in the cubic case, we normally write B, but we don't write B because A and B are the same length. So you just make sure that you understand. So typically what is done in the cubic case, but we will just, okay, let me just follow the book, and so that since you already, just do it like I've done in the book. That's what I've done there. This is your A, this is your B, and this is your C. Okay, that's A, B, and C.
Just make sure the C has a dot in the middle.
So let's just do this. So this point here. So we just draw these planes. So these are the 1, 0, 0 planes. Planes. Then you can just draw all the planes. Let me just keep this with me. So this is the 1, 1, 0 planes here. This is the 1, 1, 0 plane. And I did, I think, in the book, the 1, 1, so the 2, 1, 0. So here's the 2, 1, 0. So now we will do the reciprocal lattice. The reciprocal lattice of this, we use the mathematical form, even though it's quite obvious in the cubic case, but it's B cross C divided by the volume. What is the volume of the cube? If each of the side is A, it's A cube. So keep that in mind. So it's B cross C. So here's B, take the cross product here, there's your A star. The same direction as A. B cross C is A star, and B cross C is A. If each of the sides is A, this is actually if each of the sides is A, this is A squared divided by the volume, you get 1 over A. Okay, so the distance of this is 1 over A, and the B star is C cross A. So you take the C cross A, it is also along the direction. And then C star is A cross B, it's also over the direction. Okay, so that is the simple way to draw that, and now you can create the lattice. So this vector now, what is that one? What is that? So, okay, one of the conventions is that in the reciprocal lattice, each of these lattice points are written, so this is one, we just use a different color so it's clear. So this is 1, 0, 0 in the reciprocal lattice. We don't use any brackets in the reciprocal lattice. So we use the
How do you know it's 100?
What is A star? A means 100. This is the reciprocal lattice of A. A is the unit cell.
The vector. Okay.
Yeah. A is the unit cell. 100 is the A vector along the A. So that's 100. And the important point here is that you don't use any brackets. So that the convention is that in the reciprocal lattice, when we write 100, we already know it's a reciprocal lattice. In the real space, we use all the brackets. We've used up all the brackets that the computer has. So we have only one left. And therefore, there's no. What would be this one? 0, 1, 0. So now it's vectors. So what is this one then? 1, 1, 0. What is this? This one here. 2, 0, 0. Now you see that 2, 0, 0 is twice the length of 1, 0, 0. In real space, that would be the 2, 0, 0. Half the length. Whereas here, it's twice the length. That's why it's called the reciprocal lattice. You have a question? Speak up. Yeah, just ask. There are no bad questions. If something is not clear, just ask.
No, it's okay. I just need to stare at that for a little bit.
Okay. I won't erase it and let you stare at it. So there is your 2, 0, 0. What would be this one? 2, 1, 0. And so on. Now you get the idea. Right? So you can generate the whole, and then the reciprocal lattice are all there. Well, so, and then there's one more notation. This is G1, 1, 0. This is reciprocal lattice. Okay, I put this. So this vector is the 1, 1, 0, the reciprocal lattice vector. This vector is the G1, 0, 0. And so on. And this would be the vector G2, 2, 1, 0. So these are now the vectors, these vectors are given, these are the reciprocal lattice vectors. And the planes are perpendicular to this. The spacings of these planes are given by the length of these lattice, the reciprocal lattice. So basically what we have taken the crystal and sort of inverted the crystal and created another lattice that now tells us the key information that we need for diffraction. These spacings are given and the angle, the orientation is given. So we have taken the crystal and redone it, represented it in a form that gives us all the useful information for diffraction. There are some interesting things if you calculate the reciprocal lattice of well-known crystals. So if you take an FCC crystal and you just do the same exercise and plot the reciprocal lattice of the FCC crystal, what would you get? Does anybody know? What sort of a lattice would you get? Take a guess. It's a very easy guess. If you take a reciprocal of the FCC lattice, there's only another cubic system that you will get. It has to be cubic, yes? That much by symmetry. Get a BCC. Take the reciprocal of the BCC lattice, what will you get? FCC. That's a very interesting thing. So cubic, you get a cubic, FCC. It has to keep the cubic symmetry, even the reciprocal lattice. It has to keep the cubic symmetry. So you take the reciprocal and FCC lattice, you get this. Take a BCC lattice. You want this as a homework problem? I can give it to you. So it's pretty straightforward to calculate. You calculate the interatomic spacings, you draw the normal to the interatomic spacings, and you just calculate the lattice. You generate the whole lattice. You're perfectly capable of doing this. Apply this simple formula, and there you are. You have all the spacings, and you can calculate. You'll just see that you come up with the FCC. Okay. So now we are able to address something that I already mentioned. And I showed it you as a physical example. Now we can actually do this mathematically. What I showed you, physical example, is what I call the zone axis. So you have a set of planes, so we have these planes, we have these planes that are intersecting at some angle, and there is a common line. And this common line that is on all these, that lies on all these planes, in the real lattice, it has the common line. Let me just continue here. The common line that you see is U times A plus B times B plus W times C. This is the common line that is common to all the planes. Okay? Now, each of these little planes that you have can be represented by a reciprocal lattice vector. And since this line is common to all of these planes, the reciprocal lattice will be, for each of these planes, will be normal to the set of planes. That's how we define the reciprocal lattice. So the G vector, that is HKL, is going to be H times A star plus K times B star plus L times C star. Yes, please.
Subscript HKL.
Yes. For any vector that any, so all of these planes that are these planes, they have these planes that we have in the zone axes have indices, HKL. And so they can be represented by a vector normal to this. And since this lies normal to the planes, the dot product of these two vectors should be 0. Yes? So if it is 0, then what you have is, since let's call this vector, this line, let's just call this line L. So the dot product is also vector. So L dot GHKL should be equal to 0. And therefore, U times H plus V times K, W times L should be equal to 0. So U, H, V, K, W, L. This is the rule for that zone axis pattern that I showed you in the diffraction. You have a specific vector here. There's the direction and all the diffraction patterns, all the planes are always perpendicular to this in that particular zone. Yes, please.
Can you explain what G represents again? I'm a little, like, I understand it is you just drawn it on that square, but I don't understand conceptually what that is.
Right, okay. So we have a lattice. Okay, so the lattice, each of these points, we have an origin can be identified by a vector. From here, it tells you the position of that point and the direction. So it's a vector. So this is the reciprocal. So you can create a unit cell, just like you created a real lattice by a set of vectors A and B and C. This reciprocal lattice points also can be represented by a set of arrays of points, and you can describe them as vectors from the origin. This is the reciprocal lattice.
Okay.
So each of these points, so this when you say G210, it also tells you that it has a certain magnitude, and the magnitude is reciprocal of this interatomic spacing, and its direction is given by this.
Okay.
That's normal to those set of planes. So in real space, the 2, 1, 1, 0 planes will be like this, they'll be normal to this.
Okay.
And the spacings of those will be reciprocal of this length, they'll be like this. In real space, the 1, 0, 0 planes, because the reciprocal is so small, they would be like this, and they would be normal to the 1, 0, 0 planes. And same thing, this would be like this, and the width and the distance is the vector, the magnitude of this vector is reciprocal of that interatomic space. So we are trying to capture all of this information in one set of vectors. The orientation and the spacings and the direction normal to it. Please ask, because conceptually, if you don't get reciprocal lattice, you will get stuck in the diffraction. As you go higher and higher in more detail in diffraction, you will get really stuck. That's why I'm spending a whole hour on just reciprocal lattice today. Because people do this and they just throw this reciprocal lattice, students get lost. After a while, because we will stop talking only in reciprocal space. As long as you don't understand, if you don't understand the relationship between the reciprocal and real space, you will be lost. But the concept is not that difficult. All I'm saying is that you have some interatomic spacing, you know what that spacing is, whole family of planes, you have a sense of that magnitude. You also have a sense of the normal to the set of planes. So you take that magnitude of the interatomic spacing, you take the inverse of that, that gives you the magnitude of the vector, and this direction, you keep the same direction, just the norm. And you just plot that vector, the magnitude of that vector, as the reciprocal of the distance. And the direction is given by the normal to the set of planes. So conceptually, that is the concept. Once you understand that, then we can move forward, and that's what we will do in the next class. Quickly do Bragg's law, and once we do Bragg's law, we will then do what we consider as the important transition in terms of your sophistication of understanding diffraction, is to go into the UR sphere construction and go into diffraction in reciprocal space. That is going to be in the next class. But today I just want to make sure that any questions on reciprocal, we have still a few minutes. Please ask. As I said, there are no bad questions. It's just make sure you understand this. Yes.
When you were calculating this inverse for the tripoint, was it tripoint or?
Well, this is a tricase, the general case, the most general case.
Right. And you had originally written A star. but
Sorry,
it
there
had
was
to
a
C
mistake.
star.
It is just along the C direction. It has to be, that is what it is. This is along this C direction, that's what it is.
Right, so can you explain that again so that I'm clear?
Okay, basically what I did was, this is the C star along this direction. This is going to be A cross B. This is A cross B, and that is the area of OABC.
Oh, okay.
And then the volume of this is this parallelogram multiplied by this height OP. Not this one, but this height. And that height is area of OABC multiplied by ABC cancels. This is 1 over OP, and this is the 1 over D001. This is the Z direction. The interplanar spacing. These are the 001 planes. This is the 1 over. I'm just showing you that basically that is the inverse of the spacings.
Cool.
The way we define it.
Could you do maybe like B star?
B star would be I have to redraw this. All I basically easily do. You want me to do B star? I'll show you how to do B star. I'll show you how to do B star. That's B star. I just change it. That's your B star.
And that would be A cross C.
Yeah, exactly. So I just changed the slightly and made it B star.
Okay,
Without changing the drawing.
great.
Yeah.
And then what plane would that?
So it would be the 0, 1, 0 plane. This is the B star 0, 1, 0 plane.
Okay, so you use distance of 0.
Yes, please, Frank. Any questions?
Yes, so this is just maybe something in my head, but it looks like what you're taking is that you're taking the like infinite slices you have inside of the lattice and sort of inverting those to the outside of it in reciprocal space. So then if you have a finite sample, are you turning that finite space inside of the lattice when you turn it into the reciprocal lattice?
Well, we're not doing either one of these. I mean, so what we are just taking is, strictly speaking, if you're doing it mathematically, we are taking actually a Fourier transform.
Oh.
Okay,
Wow.
that's what we are doing.
Oh, okay.
But that's mathematically. I didn't want to get into the mathematics. I just want to show you physically the whole idea.
Okay.
So